In this demo, we're going to be querying a cool data set. This is a Bitcoin data set in BigQuery. And what makes it cool, besides the subject matter, is it actually has nested and repeated columns. So if this is the first time that you've worked with structs or arrays, this demo will be super useful for you. Again, all these demos are in our public repository under the data engineering course within demos. So let's follow along. So the first thing that we want to do is access the data sets. This first query is going to give us where the data set comes from. So inside of GCP, I'm going to paste the query there. One of my favorite things is one of the shortcuts that you can do. I'm on a Mac, so if I just hold the command key down, I can highlight all the tables that are in the query. So if you're just given a query from a demo, you can see we've got Bitcoin public data set as a project. The data set is Bitcoin blockchain. The table name, we have two. The blocks for inside of the blockchain. Can't have a blockchain without blocks. And you've got the transactions as well. So once these are highlighted, if you click on the table name, it'll actually take you to the schema, which is super useful. So again, data set, and then two different tables. Clicking on blocks, we can take a look at how much data is in here just by looking at the metadata in BigQuery. Schema, those are the different columns that we have available. A lot more on that in just a second. Let's see how big this data set is. It is 0.5 terabyte, 540,000 rows of blocks that are here. And as you see in a minute, you can have multiple transactions as part of a Bitcoin block that's solved by Bitcoin miners. You can actually see that when you preview the data. If you haven't seen nested and repeated fields before, this may look a little surprising. So let's see, I'll zoom out just for a little bit. And you can see one row ID, and you got the block ID. It's just an identifier for the individual block, which is a record on this shared distributed ledger that is blockchain for the specific Bitcoin network. And if you scroll over, you see a lot of gray area here. What's going on with that? Where's row number 2? Well, row number 2 doesn't show up because you have different levels of granularity inside of the same data table. And this is because you have nested data and repeated columns in there as well. So you can see for a given block, a block can have more than one transaction. So this block ending in A3876 has multiple transactions as I scroll to the right. It has, as part of this, miners have confirmed that this Bitcoin transaction, either sending or receiving Bitcoins, is in there as well, and ending in 89, ending in 95, a few more as well. So it's kind of like if you've used merged cells inside of Excel or Google Spreadsheets, similar concept. This is a nested field because it has a prefix transaction, it's .transaction ID. That means it's a struct. And it's a repeated field because you can have more than one value. And repeated, when you hear that word repeated field, immediately think of the data type arrays. So how do you query this stuff, right? So we've got our query here. We're going to give us the block ID. You saw that one. There's multiple sequence numbers that could be a part of the block. We want the latest, the maximum. And also, as I mentioned before, you can have multiple transactions, Bitcoin transactions that are part of a single block on the register. So we've got blocks, and as you saw here, the first query, we're not going to use this nested column. We're going to pretend like the transactions struct, transactions dot whatever, transactions dot inputs, transaction dot transaction ID doesn't exist. We're actually going to just join on a separate table, a transactions table that also has this same information. And this is more typical if you've used relational schemas before and you've got just another table that you just do a join against using a common key. In this particular case, it's block ID to get the count of those transactions. And we're going to show you, yes, this will absolutely work. And we're going to query it. But as the demo is going to tell you a little bit, you want to look at the slot time consumed. That's how much kind of compute power distributed in parallels behind the scenes, and the bytes shuffled, which is those VMs behind the scenes talking to each other. So it processed about 48 gigabytes, did it in about 12 seconds. Under execution details right here, you can see if you were going to process this in linear on just one machine, it could take 2 hours, if not more. And we had to shuffle around 18 gigabytes of data in order for all those VMs to talk to each other and get that data in there. And largely, you can see as you scroll down, most of that work was done in the join. This is the query kind of execution plan. You can drill open and get a little bit of the pseudocode of how it actually runs behind the scenes and processes that. So showing now that you know that inside of that table, you don't need to have the transactions as a join. It's already part of the table in a wide schema. As part of blocks, you also have this transactions struct. A struct is just a container for other fields. You can think of it as a table that's already been pre-joined. To further illustrate that point, going back to the schema, you can scroll down, you can see anything of type record is a struct, struct, and that is not unique to BigQuery. That's generic SQL. BigQuery supports it, and you can see transactions. That struct has a bunch of different nested columns as part of it, and some of those columns happen to be repeated. What that means is structs can have other structs as their children. So transactions dot inputs dot something else. And those children, those column fields can also have they can be repeated, meaning that their column type is an array of strings, an array of integers. You're going to see what that means in the later half of this demo. So let's paste this. If you remember, that was shuffling a lot of query bytes. Now, instead of doing the join, you notice we only have one table here. And it processed in 0 seconds. That's because I ran this before. It was cached. Anytime you're doing a performance demo inside of more query settings, you can disable cached results as well. Wouldn't that be great, right? So let's see. It took about 12 seconds for the first query to run. It was processing, I think, about like 40 gigabytes or something like that. So we're going to see what the performance improvement is. So it's a little bit faster. It's 7 seconds. About half the data that's being processed. And you can notice that a dramatic shift in the number of bytes shuffled because all the data is in one place. BigQuery supports what we call denormalization, having super wide schemas in a single table because BigQuery is column-based. And you can see we're not shuffling gigabytes of data anymore. Like, I can't remember what the last number was 40 gigabytes or something like that. But the amount here that we're shuffling is just megabytes, 88 megabytes, very trivial amount. And as well as the slot time consumed, this isn't 2 hours, it's just 9 minutes. So it's much, much, much faster to do the query instead of doing the join, to have this separate nested field via the struct inside of there as well. So that's how you query it. For those following along at home, if you're wondering, like, from this table as B, comma here, the comma actually is the exact same thing as saying a comma is an implicit cross join. Inside of the world of structs, this is a correlated cross join. So the analogy is you have multiple tables. Conceptually, you can think of these as tables, multiple child tables as part of a parent table. That's how I like to think of it. So your structs, these record values, are kind of like multiple tables within the same table. And in order to access their columns, you have to do what's called a correlated cross join. So you can write it out cross join. Generally, folks just exclude that. And when you need to unpack these struct values, you can just do the comma into them. And that's how you get the values out of the struct. So it's similar to joining, except you're not joining on any other tables. There's no join command inside of there referring to another table. Okay, part 2. That's explaining structs, and you can see that's much faster and processes a lot less resources. But that just covers the nested part. The repeated part is what's super interesting to me because you have different levels of granularity. One block, as you saw previously, has multiple transactions inside of it. Let's find something interesting. So you're going to learn a little bit about Bitcoin here, but don't worry, it'll apply to any of your data sets, even if you're not working in cryptocurrency. So what we want to do is, inside of this data set, I'm going to pull open this query. Inside of this data set is a total amount of Bitcoins that are trading hands as part of the distributed ledger here. So I'm going to open up the blocks and let's preview the table. And the actual output column, how much is done in this transaction. Let me zoom out a little bit. So that's the block ID all the way on the right. And again, this is a public data set, is what's called output Satoshis. Satoshi in the Bitcoin world is, I think, if you multiply it by this number here, it's the smallest atomic unit, so you can't get below 1 Satoshi. If you multiply it by this number here, which is like 1E8, I think, you can convert this. It's a direct correlation to an actual value in Bitcoin. So you always see huge dollar. It's kind of like cents versus dollars if you're in the U.S. So we want to get the block ID. We want to convert this timestamp numerical value into a timestamp that we can read. We want to get the transaction ID, and we want to get the value, the original Satoshi value, and then the actual BTC or Bitcoin value. Same thing as before. We want to get the highest amount of Bitcoins in a given transaction, the top 10. So you see it's the same thing as before. We have a struct that has transactions, and we also have a struct that has inputs. That's fine. I don't think we actually need that because we're not actually doing anything on the inputs. But when you run this, you're going to get the extremely popular error that says can't access some field with the type array. Inside of there is a integer repeated value. So what does that actually mean? So you get that error and you did your correlated cross joins as we talked before with the comma, and you're previewing things, and you're going, wait, what? I just literally, it's literally called outputs.output Satoshi. That's literally the column value here. What's going on? I already did my unpacking of transactions, b.transactions as t, so it's t, yep, dot outputs, great, absolutely. What's not working? Well, you see that there's multiple for a given transaction. So where's the transaction? Transaction ID is right here. So this one, follow it visually as we scroll to the right. There's multiple possible output values for Satoshis for a given transaction ID. So you have data that's on two different levels of granularity. So the first thing that we have to do is we have to unnest or unpack this array of values and get them on individual rows. So row 1, row 2, row 3, because right now they're all nested up in an array as part of one row. How do you do the unpacking of arrays? Well, that's with the unnest command. So what that actually looks like is we want to take the, let's find the array field. Let me just get to the S here. And we want to unnest the actual column name. It's a nested struct within transactions, much like there was transactions.inputs or transactions.outputs. We've already cross-joined transactions as t, so I don't need to type in full transactions.outputs. You can use this. This one's already been aliased. So we can use transactions t.outputs. So we're going to break apart that repeated struct. How do you break it apart? You use unnest. Give it a creative alias. I put some notes in the demo about making sure that you have correct aliases. And knowing that this is inside of our data set, it's blocks.transactions.output. Anytime you're talking dots, you're using a lot of structs inside of your data set, which helps you with the performance. And then we can literally, instead of saying the outputs there, we can just say, all right, after you've broken everything apart, this is the final result in order to unpack those arrays and get them on a single row value. So when you actually query this, you're not going to see these gray spaces anymore. Everything's going to be on the same level of granularity. And then hopefully you'll get the top 10 transactions for Bitcoin value, the timestamp, and then the block that they belong to. So let's take a look while this runs. Running. Here we go. So this block had a transaction that was the largest. How large are we talking? So that huge number of Satoshis, which I just can't convert in my head, so that's why we did it in the query, is 500,000 Bitcoin. It's a lot of Bitcoin. And on 2011. So you can see this is how you can access those array values automatically using the unnest, breaking them apart. So the last thing we want to do is say, all right, you mentioned previously that you can have more than one transaction for a given block. So how Bitcoin works is you have blocks that are solved by mathematical hashing, by these large compute power to mine and kind of solve these blocks. And as part of those blocks getting solved, there are unconfirmed transactions, people sending and receiving cryptocurrency that get recorded into the shared distributed ledger that is a block. So one block can have many transactions associated with it. And to prove that, the last part of the demo has literally just, this is the previous query that we just ran, is just taking that block that has that really large Bitcoin transaction and just saying, all right, well, what other transactions are part of that block? And can we find that? It's going to be one, if you remember that number, that 5 with a lot of zeros on it. Hopefully we'll be able to find that within this. So all I did was I found this block ID, and I just want to filter out the entire blocks table and just pull that up. And this should have the block. You can see again, one row has many different field values in it. That's where you get the nested because of the structs, and repeated because these are repeated data type values of the arrays. Multiple different transactions in here. Scrolling all the way to the right. Let's try to find that. Boom, there it is. So that's a super large value, but it wasn't the only transaction that appeared inside of that block. You can see a bunch of other transactions that are in there as well. There's a lot of interesting web resources. If you literally just Googled Bitcoin or whatever cryptocurrency network and the block ID, there's a lot of websites that literally will build web interfaces that show you a little bit more information about the distributed ledger and all the transactions for that. But for our purposes, it's just a great example to show you the differences between a highly normalized schema. Normalized means many different tables that you have to join together versus denormalized, which is where you can have a lot of what looks like conceptually tables joined within tables, like transactions. Transactions.inputs has other columns. Transactions.outputs has other columns there as well. So don't be afraid if you see really, really long scroll bar schemas inside of BigQuery. That is a performance best practice.